Can you hear me well? Okay, great. Thanks for coming to our second class. This is Modern Robot Learning hands-on tutorial. This is the second class of 4 lectures that we have in this IP course. Before we begin, any questions on logistics or any questions in general? Nope, okay. So let's just go over briefly what we covered last Friday. We went through the course overview. We talked about what we're going to be dealing with in this class. We're going to be dealing with mostly 3 things: robot data collection in general, and policy training, and the role of simulation for robotics. And we're all going to be experiencing this in a tutorial session in the last 2 weeks of this course. And this is what you're going to be doing in this tutorial session. That you're going to be teleoperating robots in virtual reality. You're going to create a data set and curate a data set to make policy training work. And you're going to evaluate. And if something's wrong, you might want to go all the way back here or somewhere here to actually make it work. And we then talk about a little bit of bigger picture. We talked about how non-physical intelligence like ChatGPT can solve various different, all sorts of complicated things, but physical intelligence are still suffering to do the most simplest thing that human babies can do, like moving boxes. And we talked about Moravec's paradox, which is a widely acknowledged thing in the community, that reasoning requires very little computation, but actual sensory motor and perception skills require very much computation resources, and that is perhaps why the physical intelligence is taking much more time to experience the ChatGPT moment. And that's the main reason why the robotics community is actually aiming for a larger scale data set, just like how ChatGPT is trained. By scraping the internet, text and image data sets from the web, we want to create something equivalent to that in the robotics domain as well. So we then talked about robot data sets, and I said there are 2 types of robot data sets that we can consider. The first one is the actual data that is actually recorded from a robot. Robots doing things in the real world, and all the data is being recorded by the robot. But I also mentioned that there can be alternative sources to train robots, and there are something like just videos of humans doing things in the wild. And although these are not the data that is coming from a robot, this data set can still provide useful information to train robots. And I talked that we are going to be dealing with this topic this Wednesday. And last lecture, we just purely focused on the first definition of robot data set, actual data that is recorded by the robot. And then I talked about those data sets are typically collected and generated by a thing called robot teleoperation. And we then analyzed 4 key elements that are crucial when designing these kind of robot teleoperation systems. And then I talked about that we're going to be going through some case studies and analysis of these 4 key elements today. So that's where we're going to start today. And after that, we're then going to cover some basics of policy training that you're going to be experiencing during the last 2 weeks of this lecture. And then briefly touch upon the role of simulation in the context of robot learning. Okay, so first we're going to do some case studies of robot teleoperation systems. And I brought 2 cases. I'm pretty sure maybe one of you are already familiar with either one of these teleoperation systems. And we're going to be analyzing these 2 systems in depth to actually learn what is actually important and what is crucial when designing these robot teleoperation systems. And before we dive in, I want to actually, as you can see over here, it's called Avatar X Prize. It was a competition that happened, I think, a few years ago. And I think it's just better to watch a video of what's happening. Okay.
Right, so if you beat the previous one.
And it's okay, so it was a competition of teleoperating robots remotely. So the operators are not situated with the robot. Operators are in some other separate room, and their mission is to actually teleoperate a robot to complete the task. And the kind of task that they are.
Wild minute. Here we go.
So this is the video of the robot.
Avatar Jerry Pratt, reporting for duty. Hello, Commander Tom. Greetings, Jerry. Welcome to Planet X. Now, we have a very difficult mission here in front of you, and it will involve a lot of operator skill to complete. First, make your way to the station hatch. Locate the switch, flip it to on to open the hatch. Pass through the hatch and across the planetary surface to the power station. When you reach the power station, you'll need to locate which of the power canisters are full. Take a full canister and put it in the canister slot. This will transfer power to the asset storage area. Maneuver to the asset storage area and using the drill, open the access hatch. Reach inside and feel for the rocks that have rough edges using your sense of touch. The rough rocks are our energy abundance rocks. Pull out an energy abundance rock and your mission is complete. Now, I know that's a lot of information. How do you copy?
Gotcha. All right. Thank you. And by the way, you've been promoted. See you later, Major Tom.
Tom, before we're done.
So they are completing the task using teleoperation.
Under 2 minutes.
And as you can see over here, this is the video of the robot, and this is the video of the operator. He's wearing a bunch of devices, VR glasses, some of the robots, and this is what the operator is currently seeing.
Mission command. It's right on line with actually where Robotics was when they started their run. It beats Northeastern, and the switch is done in seamless times at 2:17, and that's exactly.
So every time they complete the task, they get a score, and it's a whole competition. And this is the winning team.
They did yesterday.
So yeah, that's the context of this kind of competition, and this, like, the main technology that powers all these competition is actually the teleoperation system. So that's one of the reason I kind of brought this as a case study. So we're going to be analyzing it. I think that there were the runner-up of this competition from Pollen Robotics. And while we're going through these videos, let's just try to analyze what are the design choices they have made for when designing these robot teleoperation interfaces. So let's first focus on this first see the video over here. They have a slightly different robot morphology than the first video that we saw. And as you can see over here, this is what the human is doing currently. They are already also wearing VR glasses and some controls, but it looks a little bit different from what we saw in the first video. And this is what the human sees, and this is what the robot does. And it's doing the same task of lifting the lever up. And while watching this, I want to analyze what is the main command interface that this operator, that this entire system is actually using to control a robot, and what exact part of the robot is actually being controlled using those command interfaces. And if you look at it, the first thing they can see is these VR controllers. And this VR controller is first of all, mainly controlling this arm over here. As you move around the VR controller, the arm also moves. And what do you think it's actually tracking, this arm? This VR controller is streaming the spatial SE3 pose of this human hand. And that has to be somehow transferred to the joint targets of the robot arm. And so that's the robot action. So that's the human command that are being sent. So what should be the action converter over there? Have a clue? Something called inverse kinematics. Inverse kinematics is a thing that kind of converts the target pose of the end effector to a actual joints, like the actual angles of the robot arm of each joint. And this controller also controls some other part of the robot, which is also the hand, right? If you see the video, the operator is clicking different buttons here from time to time, And this button press is actually has to be mapped to the different style of joint targets for, if you can see over here, there are 3 fingers over here. And so it's much more higher degrees of freedom than a single button press. So we should somehow map these button presses into those different types of grabs of us humans. And that's been done by manual mapping in this kind of teleoperation scenario. So they have different buttons like opening, closing, or I don't know, pinching type of thing. And they are mapping those kind of hand movements into different buttons. And last but not least, the operator is wearing VR glasses. And that also streams the pose of human hand because it can move around. And that also needs to be reflected by the robot's movements, right? Because as you move this way, the robot's camera should move that way as well, so we can see what the operator wants to see. So to do that, there are some joints that kind of actuates the robot's neck part. So converting an SC3 pose to a joint target, that also is inverse kinematics. So that's the other thing. And as you can see in the video, all these robots are mobile, so they have to move around in a spatial, in the map. And this teleoperator system actually uses a pedal to actually control those kind of mobile movements. And those pedal actually commands the translational speed of the mobile base. And the robot's control is actually, a robot is actually expecting a control that are wheel velocities. If there are 2 wheels, then by controlling different velocities of different wheels, they can actually move around in the spatial plane. So how do they convert this translational speed to like a wheel speed? There's a thing called differential drive controller. So this is the thing that powers these kind of action converter. So all these things combined, we kind of analyze this way of going through from human commands to robot actions. And these are all the action converters. And we went through all these kind of things. Do you perhaps see any kind of expected issues of these kind of design choices by any chance? Mm-hmm. Mm-hmm. Exactly. So inverse kinematics, although it's a very powerful thing that powers most like robotics research, but it can have some caveats here and there. First of all, the workspace is quite different. This robot arm has certain workspaces because it has certain morphologies, but human arm workspace, the workspace of human arm can be very, very different from the robot arm. Although it does look similar, but if you reach far out, for example, the robots perhaps cannot reach that far because the Pollen Robotics use is actually quite small robot. So it's quite small, like I think it's 70%, 80% smaller than human arms. So the workspace might be different. So if the human has to reach far away, then there might be some issues. But although the target SC3 pose is within the robot's workspace, there might be still some issues. There's a thing called singularities of robot arms. If you have taken like robot manipulation class or any kind of robotics 101 class, there are singularities of robot arms where the robot kind of behaves very weirdly in certain configurations because the inverse kinematics has to choose like one solution among very infinite kind of solutions, so it kind of freaks out. So having to rely on inverse kinematics can cause certain issues, but there are clever ways to avoid it. So that's how, yeah, question.
You talk about like the mapping of like the human workspace,
Mm-hmm.
workspace,
Mm-hmm.
like how do you deal with that? Is it just like, is it still like a one that's happening like I move my arm once, or like the robot arm also moves that, or is it like scaled by some like concept?
That's also a design factor. Like if the robot arm is smaller than the human arm, then the engineers might actually make a choice to scale down the movement of the humans.
Is that like standard?
Yeah, it's quite standard. Yeah, it's quite standard. And also, if the teleoperation system is designed to do very much precise task, then they might want to scale down the movements a little bit to actually more focus on the precise movements of the robot arm. And if they want to move fast, for example, then they might want to like amplify the magnitude of human movements. So yeah, that's a pretty common design choice that people make. Any other issues other than inverse kinematics that you might find in these kind of design choices? Force control.
Because we're using like a virtual
Mm-hmm.
but the data we're using doesn't account for the fact that like even if like an animation motion
Mm.
be the same, it doesn't account for certain forces, so maybe that like precise animation would
Exactly. Yeah. Yeah. For example, like I guess the most typical scenario is like when the robot arm is hitting a table, you're not getting any feedback from this VR glasses because your VR controller can move anywhere around the world. So if you just go pass by this height, your robot arm is just going to smack the table, and the operator does not know anything about it, other than having a visual feedback of the thing. So that's what we're going to be analyzing next, this way, where how the robot's state and the state around the robot is being presented to the operator, right? And for this scenario, it's pretty simple. It's just projecting the camera feed from the robot to a VR glass of the thing. But if you see, well, any expected issues just going this way? I think one of the things we just discussed, like it doesn't really give feedbacks about the touch or haptics. So it might just smack into the table or something like that. Any other expected issues? Mm-hmm.
What if like, it seems like it's wireless, right? So
Mm-hmm.
it probably couldn't go really far.
Yeah, that's a really good point. Like once we have to transmit images, which is the packet size of the data is quite large, latency issue comes into play. So there are we should actually like do some clever engineering on the network communication as well, and that actually improves the human comfort of the operator quite dramatically, reducing the latency. And also the other thing that we might want to consider is that there might be multiple cameras that are attached on the robot. Some robots have cameras on their wrists. Some cameras have stereo cameras, but those stereo cameras might be situated very far away, even far away from our pupil distance. So that engineering those kind of things and presenting a really nice to see visual view is still a challenge that people have to overcome when designing these things. And one thing I wanted to mention, I think it also is related to the feedback about the haptic and touch thing. Remember the mission, one of the mission of this challenge was to actually lift up some bottle and then try to detect whether it's full or not. And it has to pick the full one and then has to move the thing. But with only these kind of feedbacks, like we can imagine it's going to be quite hard to actually detect what's like full and what's not. So I just wanted to show what they have come up with as a solution to deal with it. Okay, I'll just.
this one and see if it happens to be full. I'm going to try to move here to the right a little so I have better access to it. Okay. I'm going to first close Swiffer and this one. Okay, so it looks like this one has a max weight of 755. Let's see if the other one is the right one. I'm going to not rotate, strike to the right, to the left a bit. Able to try to grab this canister. Oh, this one is much heavier.
Do you see what they did? How did they detect the weight of the bottles? If you see the camera feed that the operator is seeing over here, you see a little bar over here, as you can see. When it's very heavy, the bar is like fully on the top. And for the first bottle, it's only like halfway there. So they kind of designed a clever strategy to detect weights that are being grasped on the hand and kind of present it in a visual manner, because that's the only way they can get feedbacks. So depending on the interfaces that they chose to use, they can come up with some clever interfaces to learn more about the information about the surrounding environment of the robot. So that's the first analysis of this thing. And as you might have noticed, things got a little bit more overly complicated because it kind of involves the fact that the operator has to be like remotely situated. But if we can remove that assumption, which is like the video that you're seeing over here, things can be quite simpler. And this is a system that Stanford have developed a few years ago. It's called Aloha. And if you see the video over here, it's just much more intuitive system. That there is a commander robot and the follower robot, and the commander and follower shares exactly the same kinematic structure. And the operator is just holding handles of the commander robot, and it's just exactly following. The follower robot is exactly mirroring the movement of the commander robot. And if you try to analyze what's actually happening in this kind of teleoperation diagram, this action converter and an observation converter, it becomes much, much simpler. The action converter is basically an identity function because the human commands are being physically translated to joint movements because it's actually moving the robot with same kinematic structure. And the observation converter, well, there's nothing about converting observations because the operator is actually physically in the same space. So the human eyes are actually directly observing what's happening at the end effector of the robot hand. So yeah, so those are kind of very two distinct types of teleoperation systems, but many of the existing teleoperation systems out in the world is somewhere in between. For example, these Aloha system doesn't really have rich haptic feedbacks. So if it also suffers from the same issue where the follower robot hits the table, the commander operator doesn't really get much feedback regarding that. So there can be some improvements that can be made in these teleoperation systems, but yeah, these two are kind of like, yeah. It's not really. I think last year, late last year, someone actually implemented those kind of bilateral feedback from the thing. It's just a matter of setting the joint targets of the commander robot as these joint states of the follower robot. So yeah, it's not that complicated, but there's a bunch of tuning that needs to be involved to make it more seamless. Cool. So that was the first part of the lecture today, where we kind of analyzed how teleoperator systems are being designed And the reason that we designed these, we analyzed these systems is that, as a reminder, teleoperation is the de facto standard way of generating robot datasets in general. And with the datasets that are being generated using teleoperation, then we can now dive into actually training policies. While the teleoperation involves humans in the loop to actually generate those datasets, the whole point of training a policy is to actually remove that human in the loop, so the robots can autonomously do the task. Quick questions. When we are recording datasets using teleoperation, which data do you think that we are recording as a dataset? Is it going to be A or is it going to B? Show of hands. Who thinks we're recording the A part of thing? 2. Who thinks we're recording the other part of thing? Great. Yeah. I guess it depends on the design. First of all, we can record everything. That's not an issue. But the crucial part that we have to record is the right side part, because that's what is being received by the robot. So that's what the robot's brain is actually seeing. Every sensor readings that are containing the robot's and world state is being received by the robot, and the robot's brain has to infer future actions based on that. So we don't necessarily have to record this left side data, but the important thing that we have to record is the right side data. And so these S0, A0, S1, A1, Sn is actually states and actions that are in the right side of this robot. And once we actually record all those data sets, then the robot control becomes a supervised learning problem, because for every sensor readings given from the robot, the only thing that the policy needs to do is just to infer the right actions. And just to clarify, the way I formalized a policy training right before falls into the category of behavior cloning, which actually is just directly learning the mapping of the paired state and action from teleoperated datasets. But there's a larger concept called imitation learning, which also includes another topic, which is called inverse optimal control. Some people call it inverse RL, which is trying to learn more of a reward from the dataset rather than like trying to directly map actions from states. This inverse RL we're not going to cover in this course. We're just only going to be covering behavior cloning. But if you're curious, we can cover it, for example, in the last lecture very briefly if you want. Okay, so coming back to the behavior cloning problem, we have a data set, S0, A0, that is recorded again from teleoperating the robot with human in the loop. Now the problem is becoming like a supervised learning problem. What we want to do is to maximize the log likelihood of a policy where this data sets, or S and A, is being sampled from the collected data set. And we have two main design decisions that we have to make when training these policies. First one is actually engineering the input and output space of this neural network policy. We're going to go through this in detail very soon. The second thing is actually engineering the policy architecture. So let's first talk about engineering the input and output space of neural network policy. Well, what do I mean by this? There are two types of policies that are operating that we can train. Type A is actually a mapping of single state to single action. So you can see over here, it's a single state is getting passed into the neural network policy, and the policy is trying to predict a single action. Whereas type B, it's trying to consume a history of states. For example, in this diagram over here, it is receiving a history of m time steps. And it's trying to predict like a history, no, not a history, a sequence of future actions. with n time steps. Before we dive into these time step related issue, do you notice any weird hats in some of the notations? Where do you see the hats? On the states, right? I just wanted to briefly touch upon this function G that we robotics practitioners actually do before training the data sets, which are often overlooked. This function G is a function that kind of transforms the states that are recorded in the data set, which I have to clarify. The state is a combination of various different sensor readings. It might contain something like camera feeds, or joint states, joint torques, joint angles, or if the robot has some tactile sensors, tactile readings can be included in the states as well. So this is not a single vector, but it's a set of vectors that we receive from the robot, every sensors. And what this function G does is to actually choose, very carefully choose what states are we going to include to train a policy. For example, we very much often exclude some of the states that are available from the robot's sensors. If there are both, for example, if we're talking about the arm, in most cases we have both joint poses, joint angles, and both end effector pose in SC3 space. We in most cases both are available, but depending on the use case, some people might want to go just directly, just only use the joint angles as a policy input, but some people might want to use the end effector pose only. There are pros and cons for each choices, but that kind of often very much dramatically, changes the performance of the policy. So that's one thing that this function G does, and what we robotics practitioners do. And for certain data types, like SC3 spatial poses, we oftentimes transform those data types into certain vector types. For example, there are very many ways to represent a spatial pose in SC3 space, especially for the rotation part of it. Some people might want to use 3x3 rotation matrix, which the last column is kind of redundant. So some people take out the last column and just only use the first two columns to pass in as a policy input. And there are papers that are showing that just taking the only first two columns dramatically improves the policy learning performance. Yeah.
Are there any constraints on what G is? Does it have to be smooth or?
No, it's G is kind of more of a heuristic function that people, there's not really a good principle of what exactly we should do. The robotics community is still exploring ways to find a principled way of doing these kind of operations on the available sensor readings from the data set. So it's more of a iteration, experiments and see, yeah.
So you might pick G. So what do people usually pick G based on how that affects your training?
Exactly. Yeah, we just try very much very diverse things, very many different trials, and see how it performs. We might have some kind of educated guesses to actually start off experimenting on this G, but yeah, there's not really a good principle, to engineer this thing. Yeah, coming back to the SC3 transforms, rotation part of it, one way to engineer and transform the rotation matrix is to just take the first two columns, which results in 6-dimensional vector. The other way, some of you might know, there's a thing called quaternions. Some people might use quaternions that results in a 4-dimensional vector. And those things actually affects the policy performance quite a lot as well. So that's one of the things that practitioners actually engineer and try different things as well. And the last thing I wrote down is dropping out certain modalities to prevent overattention. And this actually happens when there are modalities, very much diverse modalities, for example, RGB camera feeds and also tactile sensings, which is also a form of image, which can also be a form of image. And just naively passing every state, every kind of sensor modalities into the policy might make the policy to over-attend to certain modalities. But if we want the policy to kind of more focus on the tactile readings of it, some people choose to drop for example, RGB camera feeds from time to time to make the policy to learn more from, more from the tactile readings. And so that was the reasoning behind why I put the hat over the state S over there. And regarding the time steps of history and the prediction sequence horizon, do you have any kind of initial guesses what might be an ideal combination of M and N? Who thinks just type A is enough? Or type B might be necessary from time to time? Yeah. There are a couple of different pros and cons, but for choosing different values for M and N. Pros and cons for having a single time step condition policy. Policy faces less out of distribution inputs. That is pretty evident if you think of this policy having to, if you think of, for example, it's type B, if M is like more than 1. We are expecting this policy to be learning a mapping from much larger space in general. For example, if this ST is like 6 dimensions in total, this type A policy is expecting to generalize over 6-dimensional space, right? But as we increase the time step that the policy is expecting to see, for example, if you're expecting 5 time steps, we're expecting the policy to generalize over inputs that are spanning across like 30 dimensions in total, right? So as we kind of pass in more and more time steps as an input to the policy is more likely to face out of distribution inputs during its evaluation phase. So that's one of the pros that we can get when we're choosing M equals 1 in this policy. And it also, if we choose M equals 1, it also enables reactive failure recovery behaviors. And what I mean by this is that, for example, when the robot has failed to do the task and has returned to the same state, if it's conditioned on a history of states, then the policy might just freak out because the data set didn't really contain anything that are trying to recover from the failure history. But if the policy is only conditioned on a single time step, when it's actually coming to if it actually came to the right state, then the policy then knows how to recover from the state because it can retry doing things again that the operator have done in the same state during the teleoperation phase. So setting M equals to 1 enables nice reactive and failure recovery behaviors in general. And the pros and cons of having larger time steps. It is less prone to compounding errors. Does anyone know what the compounding error means? Mm-hmm. Yeah. Mm-hmm. Yeah, kind of similar. Like a compounding error actually, like imagine a policy. Policy is going to have some errors, right? It's not going to like predict the like exactly right ground truth actions. It's going to have errors, but as we pass in those errored action to the world model, for example, then the next state, ST+1, will slightly deviate from what we have seen during like expert demonstrations, right? And if we repeat that process like multiple times, it is very likely that the trajectory of ST+1, ST+2 like very largely deviates from what we have seen during the expert demonstration. So that actually causes a lot of problems. That's the like major problem of doing behavior cloning in general. But and that is becoming more and more exacerbated if the feedback loop is very tight. For example, if n equals 1, those compounding errors are accumulated for every time step, right? So it's going to very much likely to deviate very quickly to an outer distribution area that's outside the support region of the collected expert data set. But if we increase the time step and let the policy predict a little bit slightly longer horizon, open loop actions, then those compounding error issues might be like mitigated because the first predictions that is being made at ST, if the ST is staying in the support region, in the in-distribution area of the expert data set, then those action predictions will be quite reasonable. So it's kind of, as you make the policy to predict a longer horizon of actions, it kind of reduces the opportunity of those errors being compounded. So that's one of the reasons why people choose to use larger n larger than 1. And also for the same reason, it might be less vulnerable to disturbances. But one of the downside, coming back to m equals 1, one of the downside of doing conditioning the policy on a single state inputs is that the policy has to deal with multimodal output distributions. We're going to be talking about this very soon. And one of the downsides of having the policy to predict larger chunk of actions is that the policy becomes less reactive because we let the policy to run for a longer horizon, a longer period of time without getting any kind of feedbacks. So if any kind of incidents happen that needs kind of corrections during those kind of execution time, then the robot will not be able to do it because it has to execute all those actions being predicted by the policy. And also, although there are ways to mitigate this kind of problem, just naively speaking, these kind of larger chunk actions will make the robots to behave a bit more jerky because the predictions kind of, we're executing one prediction and then recalculating and then executing another prediction at that time. So the predictions might look slightly different. So we might result in a very jerky behavior. But there are ways to mitigate these kind of problems. And coming back to the multimodal, and a paper also from Stanford, I didn't put the citation in it, did some experience on the effect of this n, the value of n, and they have found that n equals 1 performs like very worse than some certain number, n equals 100, for example. And general rule of thumb of setting n is to set the policy to predict like 1 or 2 seconds of actions. So if the robot is running at 60 hertz, then we set the policy to predict 60 time steps of actions for every time step. So that's the thing. And then now we're going to talk about the problems of dealing with multimodal output distributions. And this is the video that I brought as an exemplary video that kind of shows how multimodal the expert demonstration that can be. So this task is to actually put the T into this box by pushing this kind of, it's a very simple 2D plane task. But as you can see over here, like this operator might have gone either this way and put it in that way, or like move this way, or so basically this kind of task actually shows how diverse and multimodal the expert demonstrations can be at certain time step ST. And this is actually a visualization of it. Some experts actually go this way to actually move the T back into the goal pose. Some people move this way to actually make it to complete the task. The reason I brought this example is that this actually is a really good segue to talk about policy architectures, because these some of the policy architectures are really good at like modeling this multimodal distributions, but some of the policies are not. So that kind of leads us to talking about engineering the policy architecture, which was what I mentioned as a second design choices that we have to make when training policies with teleoperated data sets. And before talking about architectures, I do want to differentiate two things, because I kind of saw some people like confounding these two terms. There are policy architectures are slightly different from talking about neural network architectures. Policy architectures, I think I wrote this down as a definition, differs in a way regarding the mathematical formulations used to generate action predictions. For example, some people might want to use diffusion models to make the predictions based on the inputs and produce the outputs. Some people might want to use variational autoencoder, VAE, or not a lot of people are using GANs for robotics these days, but people might want to use GANs. So all of these are classes of generative models. So these are the type of architectures that we are talking about. These are the type of generative models, but if you want to do a pure regression problem, then we can also do a non-generative version of it. But that's also a choice that we can make when designing policy architectures. And that is very much independent from the architectures that we use for neural networks. And the choice of neural networks actually determines how we encode and decode the inputs that are getting passed into neural networks. So that is actually a decision between just using pure multi-layer perceptron, fully connected layers, blah, blah. Although transformers also contains a couple of MLPs, but people can choose to use transformers as well. So diffusion policies can use either MLPs and transformers as their backbone. VAEs can also use MLPs or transformers as their backbone. So differentiating these two might be worth noting when reading the literatures of robot learning. And talking about, I'm not really gonna go deep into the actual generative models and the mathematical formulations of the common generative models that are being used in the robot learning community to train policies. I think the two, it's either a pure regression problem, but if you go to the generative model route, I think there are two types of generative models that people use. One is variational autoencoder, and the other is diffusion models. And I'm just gonna briefly mention about the pros and cons of each models. So for example, if you might wanna just practically want to train robots to do things, this is what you have to be thinking about when choosing between these two things. Variational autoencoders, it's very, very cheap to compute because it only requires one forward pass to generate action predictions. But the cons, compared to diffusion models, it really cannot really model multiple, like extreme multimodality. Although there are ways to make it model much more extreme multimodality, but the original form of it, it can only model some, yeah. In terms of expressibility of multimodality, it's way less capable than diffusion models. Diffusion models, like pros and cons, are exactly flipped. Pros is that it has very much expressive powers, but the cons is that it's very much expensive to compute. As if you know a little bit about diffusion models, it has to go through the denoising phase to actually generate the outputs, and they have to go through those denoising phase multiple times to actually generate good quality examples. So it's in terms of compute requirements, they have to forward pass way many times than having to pass through a single VAE model. Yeah, so those are the two things that we have to be aware about when training policies with teleoperated datasets. One is actual training methods and designing this input and output space of policy learning in general, and policy architectures. And I wanted to emphasize designing policy architecture and choosing policy architectures are different from choosing the neural networks that are powering those policies in the back end. Yeah, I'm going to pass this. And in the final part of this lecture, we're going to be going through the role of simulation as well. And before talking about simulation in general, I want to mention why, the reasoning why we want to focus on simulation. And to do that, I wanted to actually go over and emphasize the actual cost of doing real-world teleop data collection, which surprisingly a lot of startup companies are doing. If you know a company called Physical Intelligence, they're also doing those kind of things. Google DeepMind has a bunch of robot farms, and they're hiring a bunch of teleoperators. And what all these companies are doing is to, first of all, buy a bunch of robots to teleoperate. And I wanted to say, robots are not cheap. It's very much expensive. So it requires a lot of money to actually set up that artificial farm of robots to begin with. And then they actually have to physically set up environments around the robot to collect the task for. And option A is to actually physically move the robot to different places around the world. And for example, TRI, which is right next to us, Toyota Research Institute, is actually renting Airbnb places to move their robots and collect data sets in different households, for example. And there's also option B, is to, if option A takes up too much time and effort and money, there is option B to actually set up a fake environment around the robot in the lab space. So we either have to do option A or B to actually set up the environment and to collect tasks. And once we have set up the task, what we do is to actually hire a part-time or full-time teleoperators to come in and use the teleoperation systems that they have designed, which we covered in the first part of the lecture, to collect the data sets that can train policies. And then those teleoperators come in regularly, part-time or full-time, and then they complete the task and generate data, basically. And after every completion of the task, they have to reset the environment. For example, if the task was to clean up the environment, clean up a messy kitchen environment, when they completed the task to clean up the kitchen environment, they actually have to create a messy kitchen environment again to actually create another round of robot data sets, robots cleaning the kitchen, right? And this endless repetition just happens until the policy training team says, oh, we have enough data, you can just go home or move on to the next task. And this, as you can see over here, involves a lot of efforts. For example, set up the hardware, set up the environments. And although this resetting the environment, this is often overlooked, but it is a much difficult thing to do than one expects. Like, how are you gonna mess up the kitchen every time you clean up the kitchen? Like, it's a whole other process that you have to go through. So this, although a lot of companies with big budgets and big resources can actually afford to do these kind of things, it is not really easy to do this in general. So people are starting to ask the question, can this actually really get us to the scale that we need to train ChatGPT models for robotics? Because those large language models are being trained on really, really massive scale data sets, but people are starting to wonder, can this regime of creating robot data sets can really get us to that scale of data set? So people are the committee is trying to explore some alternatives of collecting data sets without requiring actual real-world teleoperation. And these two modalities are going to be dealt in the lecture two days later, and Wednesday. But today we're going to be talking about using a simulation as an alternative virtual world that kind of circumvents the issue of having to rely on real-world hardwares. And this, I think I showed the video before, this is one of the platform, and all the other people in the committee are also exploring similar kind of approaches as well, which kind of uses simulation and virtual reality as a way to circumvent the requirement of having to rely on expensive hardware robots and having to set up a physically set up environments and having to manually reset the environments, because in simulation, resetting the environment can be done by just clicking a button in the interface. So these are the things that we can do. And one of the things that I want to emphasize is that the demos collected in simulation also can be very nicely integrated with reinforcement learning frameworks that kind of leverages the fact that simulation environments can be massively parallelized. This is a thing called NVIDIA Isaac Gym, which can create massive scales of robots, like 16K robots in a single environment that is very much suited to do on-policy reinforcement learning algorithms. And if we collect the demonstration data sets in simulation, it can really nicely fit into those reinforcement learning algorithms as well. And one of the reasons that simulation allows a nice and easy way to integrate with reinforcement learning is the fact that simulation allows access to oracle states, which we often call privileged states, which means that those states that are hard to retrieve from real-world sensors. And those include something like exact object poses. For example, if you have to manipulate this kind of microphone receiver over here, in simulation, if we have an object modeled inside a simulation like this, we can directly receive the state of this object, pose and velocity of the object, because that's what physics engine is using internally to simulate the physics phenomenon. But if the real robot has to infer the actual poses of these kind of objects, it has to go through some pose estimators that are trained offline with some different techniques, and those are kind of known to be error prone. So yeah, the fact that simulation demos have access to those privileged states, and including something like contact forces and contact pairs, very much nicely makes those demos in simulation to be nicely paired with algorithms like reinforcement learning that can leverage the power of these kind of features of simulation. But using simulation comes with a small cost, which is mainly two parts that I've written down over here. Is the fact that, first of all, we have to design scenes inside a simulation. For example, if you want to import this kind of microphone receiver inside a simulation scene, we either have to get a CAD model from this manufacturer, or we can use some 3D scanning apps to import this real-world object and put it into a simulation. So that's one kind of cost that we have to pay to use the power of simulation. The other thing is sim to real. Like if the policies are learned inside a simulation, we then have to go through a process called sim to real, which is just overcoming the gaps between the simulation world and the real world. And the remaining part of the lecture will briefly cover these two parts of costs that are involved using simulation. So this is a typical workflow of training robot policies using simulation. So first of all, we start with a desired or target environment and task. This can either come from our mind, or it can either be exact environment and task that we actually want to model as a little twin in the simulation. For example, if we actually want to train a robot that just manipulates things in this classroom, then the simulation scene design has to. The mission of simulation scene design is to actually create exact digital twin of this classroom and import it into a simulation. And once we pass through the simulation scene design phase, we have access to a simulation environment, and then we can create data inside the simulation environment. And using the data generated, we can train policies with it. But these policies are trained with policies that are generated with data that is generated inside a simulation world. So that has to go through a sim-to-real pipeline to actually make it executable in the real world. And if we consider these two loops as an tightly integrated loop, that's a thing called reinforcement learning. Reinforcement learning, there's no human in the loop involved during generating data. It kind of autonomously improves the policy itself by maximizing its reward, but that's a side thing that we can cover later in the course. So yeah, so two things I wanted to mention is simulation scene design and sim-to-real problem. And there are two types of ways that we can import scenes and generate scenes in simulation environment. This is one of our works one of the work that our group did. How they designed. So I want to show you how they scanned the environment. So Marcel here is using an iPhone 3D scanner app to scan 3D environments in the real world, and for some objects that require certain fidelity, they use another object scanner app to create a 3D object model, and what they do is to import those kind of 3D scans as a simulation environment. And if for example, this toaster, if articulation also has to be modeled. For example, there is a single joint that we need to open, right? That is also being manually added in this GUI over here. So yeah, that's one way that we can do a simulation scene design. And there are, the robotics community is actively researching ways and advancing, developing techniques that we can do these kind of scanning in a much more seamless way that doesn't require kind of, yeah.
I'm kind of curious because I've already tried something like this before.
Mm-hmm.
How do you isolate out, so we do this game, get a single point part of the environment, isolate out, like, for example, just the toaster oven, so you can, how do you do that?
To be honest, I'm not really an expert of like scanning 3D objects, but what we do as a robotics practitioners is just use default scanning apps on iPhone. But yeah, I'm not really sure how they.
It looks like in these videos you can actually interact with those things.
Mm-hmm. Yeah.
And like I've never been able to do that.
Yeah. For in this paper, the way they kind of differentiated the door and the other part of it is just to do manually cut the mesh. It's not automatic, but the community exploring ways to make that process more automatic. Yeah. And the other route that people go through to actually design scenes is to use generative models, for example, to generate scenes from either text prompts or image prompts. So it's not actually creating a digital twin of an environment that exists in real world, but this kind of work is trying to generate simulation scenes that looks plausible based on the text or image inputs that people have made. So as you can see over here, where is it? they are using some off-the-shelf 3D mesh data sets, and they are querying GPT models to select the right data set, select the right mesh model based on the text prompt, and what they do is just to place those selected assets in the right location and create a task. Although it's very rudimentary right now, but the community is actually doing a lot of research to make this more, make this kind of pipeline to create more realistic scenes. Cool. Okay. So that's the simulation scene design part of it. And the last thing that I wanted to talk is the sim-to-real pipeline. And there are two major sim-to-real gaps that we have to deal with. And first of all, first gap is the context dynamics. And the context dynamics gap actually means the gap between how the physics engine models physical context versus how our actual world models physical contexts. And you can see the diagram over here. The physics engine psim, I put it over here as a context simulator, accepts two parameters in general, parameters related to the context solver, because physics engine internally is just a bunch of solvers that just doing some non-convex optimization, all those things. And those solvers have a bunch of parameters that we need to tune. So solver parameters are accepted as a hyperparameter, and physics parameters, including something like friction, or if it's deformable, Young's modulus, those kind of things. So when these two parameters are getting passed in as a parameters of this physics engine, then this physics engine accepts ST and AT and outputs the next state by solving all those context-related stuffs. But the problem of the major gap, major sim-to-real gap is stemming from the fact that this context dynamics psim, which is ST+1 condition on ST and AT parameterized by say these two variables, is sometimes very different from the context dynamics that we get from the real world. There are two ways to solve this issue. First is what we call a system identification problem. In short, we call it SysID, is to actually find and optimize these two parameters to actually match it to the real world's context dynamics. There are many ways to do this, but one of the ways we can do is to do it in a data-driven way. Using the massively parallel simulation, for example, we can do some evolutionary research, for example, on these two parameters, and actually try to match the trajectories that are being generated inside the simulation environment and also the real world environment. So some people are trying those kind of things as well. But some of the parameters cannot really be accurately measured. For example, the friction parameters, it's really hard to measure really accurate friction parameters of certain objects in the real world. So in those scenarios, what we do is to actually make the simulation engine to just randomly sample these parameters from a fixed range so the policy can be learned to robustly act and behave in those kind of a reasonable range of these two parameters. So in general, system identification and domain randomization, as a robotics practitioner, we do like both in many scenarios. Yeah, and if we get it right, these are the results that we get as a sim-to-real policy, sim-to-reeling a policy. There's also a work from our research group a few years ago from Tao. So the policy here is actually trained to reorient this object into the right orientation, and every policy is learned inside a simulation. And the technique that Tao has used to transfer this simulated policy to the real world is a combination of both, doing domain randomization on these parameters, but having a good guess of those range by doing some very basic system identification.
System identification, I would do that. Look at the image and then
Mm-hmm.
look at the database and say that, okay, this looks like a toy which is made of some plastic.
Mm-hmm.
So it should be having these sort of
Yeah, it depends on the kind of task. The way we do system identification depends on the task that we want, and depends on the parameter that we want to infer. But in this scenario, what Tao had to infer in this video were the actual motor dynamics parameters which is sometimes very crucial to make things work. So what Tao did is to actually generate a bunch of trajectories of motions of these robot hands doing stuff in the air, and then he actually tried to figure out the right parameter for those motor dynamics inside a simulation by just massively simulating a bunch of different values inside a simulation and just picking the right one that just closely resembles the reactions that we are getting from the real world motors. So
the system identification is always on the robot?
Not necessarily, but mostly for example, we can do some system identifications on the objects. For example, we can try inferring the friction, but we typically don't do that because inferring,
Yeah, so right now, do you generally still have to do this step manually?
Mm-hmm.
Or is there like a generated procedure for it?
What are you generating?
Or like if I were to try to infer the friction of like a material of like an object that's kind of manipulated, do I just kind of have to like guess based off of what I already know about it and do like?
Yeah, I think that's what people do. They just see what kind of material this is composed of, and then just find the right friction parameters. So that's the reason why regarding those physics parameters, we kind of tend to rely on domain randomization, because it's really hard to get an accurate guess of the exact friction parameters or physics parameters that objects tend to have. Yeah. Cool. So TLDR, sim-to-real pipeline that deals with contact dynamics gap, is mostly a combination of both, doing some system identification on certain things and doing randomization on those unknowns. And those randomization ranges are typically based on some educated guesses, like you pointed out before. The last gap that I want to deal with is the visual rendering part of it. And this is a gap that stems from the difference how the physics engine actually renders the camera feeds versus how actual camera sees the real world. It is kind of the mission to actually exactly model, exactly import the camera models. And there's also is the same problem. Like rendering engine gets two basic parameters in general. One is related to camera and one is related to lighting. This rendering engine accepts state input from the simulation and outputs an image. And also the visual rendering gap, obviously means that these two images look very much different. So we also do the same thing over here. We either find the right parameters for these things, or we randomize these things. And what we typically what we typically try to system SysID are the camera parameters, which include something like extrinsic and intrinsics of the camera. What I mean by extrinsic parameters is the actual location of the camera in the real world. So we try to locate the camera locations, locate where the camera is, and we try to randomize slightly around that range. So regarding the camera locations, we typically do SysID. But regarding the lighting, we really cannot find the right parameters to resemble like this many lights in this classroom. So for regarding lighting, we like almost mostly rely on randomizing a bunch of different lighting conditions and hope the policy to robustly act in all those kind of different lighting conditions. But things are hopeful thanks to NVIDIA and all the other rendering companies, companies that are focusing on like improving rendering qualities, that are making those kind of fancy GPUs and stuff. Yeah, like I was trying to cut down this label and ask you guys which seems real and which seems fake. But yeah, like the thing I wanted to say is like the simulation and rendering engines are becoming more and more realistic. So there is hope that this visual rendering gap is going to be closed very much soon. But there are still challenges that we have to deal with. So yeah, that's the last part of gap that we have to deal with when trying to transfer the policy trained in simulation into the real world. Cool, that was all for today. So, and to this Wednesday, as I mentioned before, we are going to be covering, Haoshu is going to be covering the policy learning techniques that are using some alternative data sources that are generated not by teleoperation, but yeah, some other alternative types such as wearable devices or human videos. So yeah, hope to see you this Wednesday. Thank you.
So does NVIDIA like produce one type of robot that can be simulated with their thing? Like if you design your own, how would you create the simulation? Would you need to create your own?
I'm not sure if I'm following.
In the last simulation, like
Yeah, this thing, these things.
So is it only able to simulate action from these types of robotic arms, or like?
No, there are like very diverse types of robot arms, and if you have designed your own robot arms, then you can also import that into simulation as well.